the previous class we were basically at this point construct the influence line for the sphere at point C of the beam. That's what we have started discussing. Okay, and then what we have seen this equation coming, that is that for shear force just left of C and just right of C, the equation we have derived. Okay, so this is what we have seen yesterday, this one. Okay, so how do you get it? So for finding out the shear force at C of this beam because of the moving load, that means when this load is just coming and entering the beam and then moving over the beam, and it is just coming at the left of the C and then it is crossing the point C, it is moving to the right of C, and then again it is moving and it is going to the support B and it is going out. So for any position of this load, for any variable position of this load, we have found out in the previous class that what will be the shear force. So we have seen that there are two conditions. One is when the load is placed within this range, that means from here to here, this is 2.5 meter. So when the load is placed within this 2.5 meter, that means when the range of the x is more than equal to 0 and it is little less than 2.5, very little less than 2.5, that means when the load is just coming to the left of C, that condition we have tried and we have seen what is the shear force in that beam, and we have noticed that shear force will come, the equation of the shear force will come as Vc equal to minus x by 10, and exactly that's what is being written over here also. See, Vc equal to minus x by 10. So this is the first condition, and the second condition, as we have seen, when this load will be moving to somewhere here. Okay, so at that point you see the load has crossed this point C, so there will not be any, while computing the shear force, will not be subtracting this unit load from this reaction, and thus the shear just starting from just right of C up to this length 10 meter, that means this is the limit where x is greater or equal to 2.5 and less or equal to 10. For that range you are going to get the value of this shear force as 1 minus x by 10, and this is being shown over here. You see, this is the shear force, exactly we are getting 1 minus x by 10. Okay, now you see if we want to find out what will be the shape of the influence line diagram, in that case what we'll have to do, we'll have to find out the values for different values of this Vc for different values of x. Now to find out these values, you see, how do you do it? To find out these values, what is happening? See, to find out these values, if you see that if I put the different values of x, so first thing you see, if I take this equation, then you tell me for x equal to 0, when the value of x is equal to 0, so what will be the value of Vc? Can anyone tell what will be the value of Vc?
0, sir.
It is
0.
going to be 0 by 10. So at x equal to 0, the value is going to be how much? 0. Now you see, at x equal to 2.5 minus, and you understand what is 2.5 minus now? 2.5 minus
Left hand
means,
side.
yes, just left of the C, just left, little left of this C. Okay, So at x equal to 2.5, this is the limit value. At x equal to 2.5 minus, so how much will be the value of BC? How much will be the value?
0.25.
It is minus or plus? It is going to be minus. There is a minus sign in front of it. Minus or plus?
Minus 0.25.
Yes. So it is going to be just like this, 2.5 divided by 10. So it is going to be minus 0.25. Is it clear to everyone? Okay. Now you see, when this load just at the left of C, then it is 2.5 minus. But you see, this limit value is here, it is 2.5 minus, and we should write here just 2.5 plus, otherwise it will be a little confusing. So 2.5 plus means just from C, and just after this C, what will happen? So again, if we find out the value of this shear force at 2.5 plus, what does it mean? 2.5 plus, what does it mean? Tell me, anyone?
So just right hand side.
Yes, just right of C. So see, when we are going just right of C, which equation I'll have to use? I'll have to use this equation, right? I'll have to use BC equal to 1 minus x by 10. Now you see, here is happening that only. So when this load has just crossed this and it has moved to the other part, you will have to take the equation of shear force as 1 minus x by 10, and for that you see how much will be the value. So what I will be putting here, 1 minus 2.5, sorry, 2.5 divided by 10, right?
0.07 VC will get.
So 1 minus, yes, 1 minus 0.25, how much will it be? It is going to be 0.75, isn't it? Clear to everyone? So see, this is having a plus sign and this one is having a minus sign, okay, and you see that's why there is a drop of shear force, and you observe here the two equations are different. That's why at 2.5 plus and 2.5 minus, we are going to have two different shear forces, and there will be a drop of shear force, okay. So this is very important to understand. You see, in case of bending moment for influence line diagram, what you have seen, in that case you see at 2.5 plus and 2.5 minus, the value of bending moment was exactly the same. However, in case of shear force, you observe very clearly at 2.5 minus, that means when the load is just at the left of C, the shear force is negative and the value is minus 0.25, whereas when the load is just crossing C and is just moving to little right of C, at that point you observe the shear force is becoming positive and the value is 0.75. Is it clear? Okay. Now you see, next step is, so the limiting value is 10. So at 10, at x equal to 10, what is going to be the value of shear force? Can anyone tell?
0, sir.
Should I put it here or should I put it in this equation? I should put it in the second equation, because I am going for this limit. 2.5 less or equal to, x is less or equal to 2.5 and greater or equal to, greater or equal to 2.5 and less or equal to 10. So in that case, your VC value is going to be 1 minus 10 upon 10. So that's nothing but equal to 1 minus 1 is equal to 0. So at x equal to 10, you see the value of shear force is going to be equal to 0. Okay. So is it clear to everyone? Any doubt? Anyone?
No.
Okay. Then let us try drawing the influence line diagram. So how do I draw it? Exactly the same way. So along the axis of the beam, let's say I take a line like this. Then you see, at x equal to 0, the value is 0. At x equal to 2.5, value is minus 2.5. So minus will be drawing downward, okay. So minus will be drawing downward. So let's say at x equal to 2.5, let's say up to this distance it is 2.5, let's say at x equal to 2.5 it is coming here. So let's say this distance say and this one, so basically this one, this much, how much will be the value of this? Can anyone tell how much will be the value of this?
2.5 sir, minus 2.5.
2.5 or minus
So 0
0.25?
point mine.
Minus 2 sorry minus 0 2 point नहीं 2.5 sir, 2.5 sir. Value will be 2.5.
Here this one I am saying, what will be the value of this ordinate?
Ordinate minus 2.5.
Minus 2.5 or minus 0.25?
0.5 0.25.
Yes, yes, yes. So this value is going to be minus 0.25. Everyone is clear? Okay. And you see this distance. So this amount, this one is going to be minus 2.5. So from here to here, it is going to be minus 0.25. This amount is going to be minus 0.25. And this distance from here to here, this distance, don't get confused, this is along the length of the beam. So from here to here, this distance is going to be equal to 2.5. So let's try to insert some, where is that text box? Let us insert some text box over here and let us see. If I put some text box over here, so let's say, so this is going to be equal to 0.25 and this is going to be minus of it, and you see, oh sorry, so see this value is going to be minus of minus 2.5. Is it clear? And the distance from here to here is how much? The distance from here to here is going to be equal to 2.5. Okay. Now what happens at 2.5? So see, just at 2.5 you are having two values, right? Just left of 2.5 you are having minus 0.25, and just right of 2.5 you are having value of 0.75. So at 2.5, just right of 2.5, again you are going to have an ordinate value which is equal to 0.75. So how do I plot it? I will have to plot it in this way. So this one will be now going up to 0.75, and you must understand this value, Ctrl C Ctrl V. So just if you go over there, so this value is going to be 0.75, and if you join it with the, where is the smart arc? Sorry. So if you join it with this straight line from here to here, see at x equal to 10 how much is the value? At x equal to 10 it is 0. So you see
0.
So this is one straight line. So this straight line, the equation of this straight line is nothing but minus x by 10, and the equation of this straight line is nothing but 1 minus x by 10, and this is what is actually the influence line diagram for what? Shear force at C. So what should I say? I will say this diagram should be said as, it should be said as influence line diagram for shear force at C. Okay, so this diagram is actually the influence line diagram for shear force at C. And have you understood it? So see, this portion of the diagram is having negative value, and this portion of the diagram is having positive value. And you please try to understand from this that the shear force diagram for the same case, when you place a load something like this on the point C, you see the shear force diagram will not come like this. If you remember, how do you see the shear force diagram? See the shear force diagram, if you place the load at C, I have explained it at the initial stage of our discussion. If you remember, I'll just go back to the slide and show you. See, the shear force diagram will look something like this, right? Shear force diagram will look something like this. And you see, for different position of the load, shear force was varying, okay? And this variation of shear force ideally will be linear in fashion like this. And for a particular point C, because of the movement of this load, the at different position of this load, the shear force at C will be varying in this fashion, and which will be explained using the influence line diagram for shear force at C. And let us go to the slide after this explanation. Let's see what happens to the shear force. Exactly whatever we have calculated, see, this one is being shown in the slide, you see, okay? So what I said, this equation is going to have, so this ordinate value is minus 0.25, that's what we have calculated, you see, minus 0.25. This ordinate value is plus 0.75, and you see this ordinate value is plus 0.75. We have explained it, and you notice this is the straight line. If you see the arrow, this straight line is having the equation Vc equal to minus x by 10, which we are getting for 0 to x to 2.5. That means 2.5 means here means just left of C, and from the just right of C, we are going to have the equation this one, 1 minus x by 10, and for that this is the equation which is being shown over here, Vc equal to 1 minus x by 10. And if you notice, both the equations are equations of straight line. However, you observe that there is a break of this straight line, because these two straight lines equations are different, and because of that, you see there is a jump of shear force from minus 0.25 to 0.75 at the point C, because of the movement of the load from the x equal to 0 to x equal to 10. Okay, so this is actually the influence line for shear at C. Okay, so is it clear to everyone? So if you have any doubt at this point, please ask. Otherwise, we will be moving to other things now. Okay. Okay.
Yes, sir.
So do you have any doubt? Please tell, because if you do not have this understanding clear, then it will be little bit difficult to understand the later part of this influence line diagram. So I hope you have got it. See, you will have to do hands-on. So don't just see these slides and whatever I am explaining, don't just see it. You just try these problems. So first problem, you try that influence line for reaction at A. Then I have given you a problem to find out influence line at reaction at B of a simple supported beam, where B is the roller support. Okay, and then yesterday I have given you another one problem where I have asked you that if a point is at a 2.5 meter distance from somewhere, and what will be the equations for influence line diagram for bending moment at C. Okay, and what will be the value of the ordinate of influence line diagram at some point in the problem I have asked you. Okay, or are you trying those problems? I haven't locked it yet. So if you
Yes,
have
sir.
submitted,
First one submitted.
yes. So please submit. Please try. See, don't think that whether you are doing wrong or right, but you try to do it right and you submit it. Okay. Unless and until you do hands-on on the structural analysis problem, you will not be able to solve it during the examination or even in your practical life. Okay. Okay. So let us move little forward and let us go to the example number 4. Now we will be coming to the application of influence line. Okay, So application of influence line, before we go to the application of influence line, let me just take the attendance at this point. So, let us take the attendance. Google Meet attendance collector, download. Attendance is taken, and let me take a screen of this and just try to clear. Okay. So let's say let's now go to the next problem, the application of influence line diagram. Now you see what you have seen in influence line diagram. You have seen that while constructing an influence line diagram, we are taking a load of dimensionless quantity of unity, right? Unit load of dimensionless number, right? That's what we are doing. And so while that unit load is moving over the beam, because of that movement of the load at a particular point in the beam, what is the effect of that movement of load because at a particular point, because of the movement of the load, for different functions like reaction, bending moment and shear force. We haven't discussed the deflection part, so it is not yet there, it is not there in your syllabus as such. So we will just discuss about three things: influence line diagram for reaction, so we have discussed it; influence line diagram for your shear force; and influence line diagram for bending moment. So all the three things for a simple supported beam we have discussed. Okay, now a unit load is moving. Now what will happen if some other load moves? See, load will not be a unit load, right? Whenever a practical problem you will encounter, the load whatever will be moving on the beam, that will not be a unit load, and the load will be having some dimension also. So to take care about that, how do I apply the influence line diagram, that you need to understand. So see, this example number 4, this is a very simple problem. You see, the solution part looks to be very simple, but before that you will have to do something else also. So see, first thing you see, determine the maximum positive live shear. So live shear means because of the moving load. Okay, so maximum positive live shear means you will have to go for influence line diagram. It is not asking you about the shear force diagram. So you will have to find out what is the maximum positive shear force in that beam developed at a point C when a load is moving on the beam, and the load in this case is given as a concentrated moving load of 4 kilonewton. So when a load of 4 kilonewton is moving over the beam, and if you want to find out the reaction, shear force, how much shear force or how much positive shear force will be, maximum positive shear force will be getting generated at this point C, then you see the thing is very simple. What you will have to do, first you will have to find out the influence line diagram for shear force at C, and which we have already solved. The influence line diagram for shear force at C, which we have already solved. You see, this problem we have already solved, and the influence line diagram for shear force at C, we have got something like this, right? And when you see, when this load will be moving over this beam, where at what position of the load what position of the load the value of the shear force will be becoming maximum. So let us again go back to this. See, this is the load moving. please try to understand very clearly. So how much is this load? How much is this load? This load, as we have assumed, this is unit load and it is moving, and because of this movement of this load we have got an influence line diagram like this. Now let's say instead of this load, control C, control V, and let us take this load, format shape, and let me change the color so you'll be clearly understanding. So let's say I change this color to this. So let's say this is your 4 kilonewton load. Let's say this is your 4 kilonewton load. Okay, now this load, if it moves over this beam, so you see what will happen. So if this load moves over this beam, then you see at every point of movement of this load, you see the load will come here left of the beam, and then it will go to the right of the beam. So at the right of the beam, when it will reach, you see this portion of your shear is positive, and this is actually your live shear. So this load, if this load's ordinate, this load value is your 4 kilonewton, and this 0.75 you have got because of this unit load. If you remember, this 0.75 ordinate of shear force we got because of what? We got because of this unit load. So what you'll have to do? You will have to just multiply. You will have to just multiply this load value with this 0.75, and that much amount of shear will be getting generated, and that will be the maximum shear when and that will be the maximum positive shear when this load will be reaching just 2.5 plus of the beam. Okay, so you see in the next part I have shown you the solution. So see, very simple. In the next part I have shown you the solution. Where it has gone? See this one. So you see, I think slides a little bit up and down. Let us go. So you see, so first construct, what you'll have to do? First you'll have to construct the influence line for shear of the beam. So that's what we have done first. We have constructed the influence line for shear of the beam at point C, and then you see what you'll have to do. You are doing nothing but the maximum positive shear force. Please understand this very clearly. Where this maximum positive shear force will occur? The maximum positive value, maximum positive ordinate for this influence line diagram is 0.75. You please understand. Okay, and maximum negative ordinate for this influence line is minus 0.25. So if this maximum positive value of 0.75, if you see, the ordinate at shear at C will occur when 4 kilonewton force will be located at what? Will be located at x equal to 2.5. That means when this load will be reaching x equal to 2.5, that means if you see from this diagram, as I have explained you, this load is entering from here, and when it will be reaching x equal to 2.5, you see it will be getting the maximum ordinate or the maximum positive ordinate value, which is actually 0.75. Okay, and when this maximum ordinate value it will be reaching, at that point only you will be having the maximum positive shear because of the movement of this load. And how do you get it? It's very simple. The ordinate at the peak is 0.75, so you just multiply 0.75 into 4, that is going to give you 3 kilonewton. So the maximum positive shear force at C is going to be equal to 3 kilonewton. Here you notice one thing. See, when you have written this value of BC for this influence line, we have just mentioned, you see, 0.75 without any unit. And when we are talking about our VC, that is when we are talking about the maximum shear force because of the 4 kilonewton load, that time I am bringing the unit into account. So 4 kilonewton load, it is multiplied with 0.75, a dimensionless number, and thus the value of the shear force will be having the unit of shear force, and the unit of shear is nothing but kilonewton. So it will be 0.75 multiplied by 4 kilonewton. This is important, okay, 4 kilonewton, and thus it is going to be equal to 3 kilonewton. Is it clear to everyone? Then I will move to next one. Any doubt?
Clear, sir.
No doubt? Absolutely no doubt? Sure? Everyone? Okay.
No, sir.
Okay. Now see, before going to the other slides, let us take the other example, that is, if you remember this bending moment one, let us take, okay, and let us copy over here, let us take it here. So let's say, okay, let us copy over here. So see, suppose you are asked sorry, suppose let's say this 4 kilonewton load is moving over the beam, okay, is moving over a beam, and at 5 meter distance from this, you are asked to find out what is the value, or not 5 meter distance, you are asked to find out what will be the bending moment, what will be the maximum bending moment in this beam because of 4 kilonewton load. So see, this load is having value of 4 kilonewton. So again you will be running this load through this influence line. Now if you run this load through this influence line, where you are going to get the maximum value? When the load will reach over here. And what is the ordinate for this? 2.5, right? So for bending moment, if you want to find out, so you tell me what will be the bending moment. So maximum bending moment, what it will be? Can anyone tell me? Because of this movement of 4 yes, tell
2.5 into 4.
2.5 multiplied by
4.
And what will be the unit? It will be kilonewton
Kilonewton.
meter. Moment unit is kilonewton meter, okay, because this is the influence line diagram for MC, okay. So see, this is going to be equal to how much? 4 into 2.5 is going to be 10, right? So it will be 10 kilonewton meter. Is it clear? So see, it's very simple. So that means if you want to find out the bending moment or shear force because of the movement of a concentrated load over a beam at a particular point, then what you have to do, you first construct the influence line diagram of either shear force or bending moment or reaction, and then at whatever position you want to find out the shear force, bending moment or reaction, because at whatever position of the load you want to find out these values, then you just put that at that position and you are going to get it. So suppose instead of this 2.5, if you are placing this load over here, so what you will have to do, you will have to take this ordinate. So if you want to find out how much is the shear force, bending moment at this point, so what you will have to do, you just find out what is the value of this ordinate, and with this ordinate value you multiply the value of 4, and that is going to give you the bending moment because of the position of this load at the point C. Okay, for a particular point C, if you want to find out what is the bending moment will be created because of a particular position of load on the beam, what you will have to do, you will have to just construct the influence line diagram, and for a concentrated load it's very simple. On the influence line diagram, for that particular position of the load, you just find out what will be the ordinate of the influence line diagram, and that ordinate value you multiply with the value of the concentrated load, and that is going to give you the value of shear force, bending moment or reaction, whatever the quantity you want to calculate. Okay, so this is all about concentrated force. So concentrated force, if you want to find out, it's very simple. Now if you have a uniformly distributed load, okay, so loads will not be always concentrated, there may be uniformly distributed loads also. So if you have uniformly distributed load, in that case what will be the method, and that you need to understand now. So let us see, it's very simple. Looks, don't get confused with this uniformly distributed load, it's also very simple. See, just you see this. So once the influence line, I have explained you this one, once the influence line for a function, so for a function means either it may be a moment function or a shear force function or a reaction function, whatever the function it may be, once it has been constructed, whatever, what you will have to do, you will, it will be possible to position live loads on the beam. It will be possible to position the live loads on the beam, which will produce, this is important, the maximum value of the function. So maximum value of the function means nothing but this one, whatever I have explained. So maximum value of the function means if you put it over here, it is going to give you the maximum value of the function. So you just multiplying the ordinate with this value. Okay, so to get that maximum value of the function, see, for concentrated load it is very easy. So we will be considering here two types of load. One is the concentrated load and other one is the uniform load. So when concentrated load I have explained you, now let us go to uniform load. So for uniform load, how will you be finding it out for a particular point, the influence of or the value of the moment or shear force or reaction at a particular point because of the movement of the uniform load. Okay, so let us see this one, this slide. If you see, looks to be mathematical and other things, but finally you will notice that this is very simple. So you see what it is there. Let's say on a beam, this is the beam, okay. So you see there is a uniform load, okay. Now if there is a uniform load, you remember whenever there is a uniform load acts on a beam, what do? We we multiply that load value with the length of the load, right? Suppose 4 kilonewton per meter, the uniformly distributed load, and it is distributed over 2 meter length, then how much will be the total load? 4 kilonewton per meter multiplied by 2, so it will be 8 kilonewton. Okay, so exactly the same way here it is being done also. So what you do, this uniformly distributed load, if you convert it to a point load, and for a very small amount of length, that is for infinitesimal distance dx, if you consider. So if you see, because of this dx, if your uniformly distributed load is W0, then what will be the concentrated force because of this? So for very small amount of infinitesimal length, if you consider, the concentrated force, equivalent concentrated force will be just like dF, and this dF will be nothing but, as I have explained you, it will be nothing but the load multiplied by the length. So uniformly distributed load multiplied by the length. Okay, now if this dF is located at x, so suppose at a distance x this dF is located, where the influence line ordinate is y, and suppose you have an ordinate of the influence line is y. Okay, so this is the beam, this is the loaded beam, and this is the influence line of beam. So let's say there is a position x, at a x distance this load is located, and the influence line ordinate at an x distance is y. So for that, what we have understood for concentrated load, to find out the influence or to find out the value of the function means here, to find out the value of either the moment or the shear or the reaction, what you have to do, you will have to multiply the load, the value of the load, with the value of the ordinate. That's what we have done. This is what exactly, see, we have done for concentrated load. We have done, this is my 4 kilonewton load, so this is the value of the load, and this is the ordinate of the influence line diagram. So exactly the same we are doing here. So this is my ordinate of the load, this is y, and this is the equivalent concentrated load, that is df, which I am converting from the uniformly distributed load, and df into y is going to give you the influence line, the value of the function, right, from the influence line diagram. And this df into y, so df, if you replace with this w naught dx, so this equation is going to be w naught dx into y. Now you see, this we have considered for a very small length dx, right, very small length dx. So if I want to find out, if I see this df, if I see this total load as summation of all these df's, summation of all these small df's, then what I'll have to do? So what I'll have to do, the effect of all the concentrated force, that means which concentrated force? This small amount of concentrated force, that is df. So the effect of all this concentrated force thus can be determined. How can you determine it? You'll have to sum it up, and sum it up means you'll have to integrate it, okay? And for integrate, what you'll have to do, you integrate over the entire length of the beam. So for whatever position you want to find out, for whatever amount of length you want to find out, you just integrate over that length. So if you integrate over that length, so what it will become? W0 into y into dx. Now you see, W0 is a constant term, so it will come down, it will come out, and so you are going to get an equation W0 integration of y into dx. Now you see, this very simple to see. See, what is this integration y dx? See, integration y dx is nothing but y is this one and dx is this one. Y is the ordinate of the influence line diagram, and dx is just the small length of this influence line. So y dx, you see, y dx is nothing but the area under this influence line diagram. So if you integrate this total y dx, so small part of y, if you take small part of y dx, if you take and sum it up, then it will be basically integration, and this integration is nothing but is equivalent to the area under the influence line. This is very important to understand. So the total area under the influence line diagram you should consider, and thus in general the value of the function caused by a uniform load. So what is the value of the function? The value of the function is nothing but the value of the moment or shear or the what is called reaction at a particular point, which will be caused by the moving uniform load, that will be given by the area under the influence line x intensity of uniform load. The area under the influence line multiplied by, so this is basically multiplied by the intensity of uniform load. So what you'll have to do, you'll have to just multiply, you see. So this integration y dx is nothing but the area under the influence line diagram, right? So you take the area under the influence line and you just multiply this area under the influence line by the intensity of the uniform distributed load. So this is actually W0, that is actually intensity of the uniformly distributed load. Is this clear to everyone? This mathematical formulation is clear? Have you understood? Any doubt? Is it clear?
Yes, sir.
Okay.
Sir.
Yeah.
Sir.
So let's take another one example, so it will be more clear. If you do not understand this example today, because we have another 5-10 minutes of this class left, so if you do not understand, again we will discuss it on the next class. But conceptually you need to be very clear about these things, okay? Otherwise then you will see the influence line problems are nothing. It's very simple to solve, okay? So let's see the next problem. So I have taken that same problem. I have taken this same problem. See, most of these problems are taken from R.C. Hibbelar's book. Okay, most of these problems are taken from R.C. Hibbelar's book. And if you, I have shared, all of you have got that books, e-books I have shared.
Yes, sir.
Yes, sir.
Yes, sir.
So go through those
Yes,
ebooks.
sir.
Okay, go through those ebooks. Okay. So in
Yes,
that
sir.
R.C. Hibbelar's book is also given. However, you may notice that in R.C. Hibbelar's book some pages are not visible. I am trying to get another one copy, but I am not getting it. Okay. So you just bear with it. If I get a better copy of that version, then I'll share with you again. Okay. So now you see, take this problem now. So see, this is the same problem. This is the same problem we are discussing here. So see, in this beam, this is a simple supported beam where a point C is at a 2.5 meter distance from A. Okay, and for a concentrated moving load, we have observed what will be the maximum shear, what will be the maximum live shear in the beam. Now you see, instead of this concentrated load, let's say if a concentrated load along with a 2.5 kilonewton meter load moves on the beam, then what will happen? So in that case, what will be the maximum amount of shear in the beam? That you will have to find out. Are you getting the problem? Let's say you have a 4 kilonewton load, and you have another one load of 2 kilonewton per meter. You have another one load of 2 kilonewton per meter. Okay. Let's say the length of the 2 kilonewton per meter load, it may be 7.5 meter, it may be 5 meter, it may be 2 meter, it may be 3 meter. In this case, in this problem, to just have the feeling of this problem and easy understanding of this problem, let us assume the length of the load is equal to 7.5 meter. So 2 kilonewton per meter load, the length of the load is equal to 7.5 meter, and so just you see this. So length of the load is 7.5 meter, means from here to here, you see this total beam length is 10 meter. So from here to here, how much? The length of the load is 7.5 meter. So you see, this load is moving, sorry. Along with that, at the end, a 4 kilonewton load is also moving in the beam like this. Okay. So along with this uniformly distributed load, a 4 kilonewton load is moving on the beam. Now because of this movement of the load, what will be the maximum positive shear in the beam? So because of this movement of the load, how much will be the maximum positive shear in the beam? Okay. So if you want to find out that, what you will have to do? See, for 4 kilonewton load, you have understood it earlier, right? We have seen it. So what for 4 kilonewton load, you see, we have found out 3 kilonewton, right? So you see, in the previous problem we have explained it, and so for 4 kilonewton load, if you remember, we have explained, so it will be 0.75 multiplied by 4, which will be nothing but equal to 3 kilonewton. Okay. Now leaving this 4 kilonewton load, there is another one load, 2 kilonewton per meter load, which is having a length of 7.5 meter, that is also moving along this beam. Okay. So then what will happen? Then you see, let me bring this influence line over here. So you see, then you see, this is the problem we have seen. This is the problem. So this problem, this is the point C, which is at a 2.5 meter distance, and this is the influence line for C, for the influence line diagram for shear at C we have constructed earlier. Now we know how to find out because of this concentrated load 4. Now we don't know how to find out for this 2 kilonewton per meter load, and we have explained through this in the previous equation. Whatever you have seen, what we have said, to find out the influence of a uniform load, what you'll have to do? You'll have to take the area under the influence line multiplied by the intensity of the uniform load. So let's go to this problem and see. So if you want to find out the influence of the positive shear, so see, this part of the diagram is positive, we have explained it earlier. So this part of the diagram is positive. So from here to here the length is 7.5. so if this load is being placed over here, what I'll have to do? We'll have to calculate the area of this influence line diagram multiplied by this intensity of load. So basically you see what is happening. Basically, if you observe what is happening, this uniformly distributed load is actually, you see, this is actually staying on this influence line like this, right? It is staying on the influence line like this. So it is staying on the influence line diagram on like this. So if you consider this something like this, then you see what you'll have to do. This total area of this and this uniformly distributed load, which is nothing but 2 kilonewton per meter, you will have to multiply this 2 kilonewton per meter with the area of this diagram, or the area of the influence line diagram. Now what will be the area where you will be placing this load for positive shear? See, this load is having a length of 7.5 meter. So you see, from here to here also the length is 7.5 meter. So in that case, the load, to get the maximum positive shear, you will have to place this load on this side. Once this load is placed in this diagram, then you are going to get the maximum positive shear value. And how much will be the area of this diagram? See, from here to here the length is 7.5 meter. See, from here to here if you go, this length is 7.5 meters. So basically from here to here it is 10 meter. So 10 minus 2.5 meter, and this is a triangle. So this is nothing but half of the base into the height. So half of the base is nothing but 7.5 meter, you see, from here. And then the ordinate value is the value of the ordinate of influence line diagram at this case is 0.75, which is nothing but the height of the triangle. So 0.75. So this is going to, this part of this equation is going to give you the area which we have understood over here, the area under the influence line. So basically this third bracket part is going to give you the area under the influence line, and you notice with that what I'll have to multiply? We'll have to multiply the intensity of the uniformly distributed load. So what is the intensity of uniformly distributed load? This is 2 kilonewton per meter. So multiply 2 kilonewton per meter and you are going to get a value of 5.625 kilonewton if you calculate. Okay. Now once you get this value, see, because of this uniformly distributed load and as well this 4 kilonewton load, what you are going to get, you will have to sum it up. So because of this 4 kilonewton load, you have calculated the value as 3 kilonewton. On the other hand, you see, because of this uniformly distributed load, by multiplying the influence line diagram area with this uniformly distributed load, you have got a value of 5.625 kilonewton. Both these needs to be added up, and that is going to give you the VC max, that is the shear force at this point C, the maximum shear force value at this point C, because of the moving load together with this 4 kilonewton and 2 kilonewton per meter, which is having a length of 7.5 meter. Okay. Now you see, now you should understand another one thing very clearly. See, in this problem we have taken the length of this load as 7.5 meter, but no, it may not be the case always. This load may be longer than this 7.5 meter, this load may be shorter than this 7.5 meter. So suppose instead of this length of the load is 7.5 meter, let's say it is 5 meter, then what you have to do to take care about the influence? You see, for 5 meter distance, if you want to find out, so you see, if the length of the if the load is of length of 5 meter, then what you have to do, you will have to place, your load can be only placed up to this 5 meter length, and in that case, you see, what you have to do, instead of a triangle, you are going to get a trapezoid. You see, so you are going to get a trapezoid like this, and in that case, if the length of the load is 5 meter, what you have to do, you will have to calculate the area of this trapezium, and the area of this trapezium needs to be multiplied with 2 kilonewton per meter, and thus this value will also change. So you see, with the change in the length of the load also, the value of the maximum shears will get modified. Okay, so basically, you see, basically it's very simple. It's nothing but you will have to just get the value of the area of the influence line diagram on which you are placing this uniformly distributed load, and just multiply with that value of the uniformly distributed load. That is going to give you the value of the function, that is either it is shear force or bending moment or reaction. Okay, so I think we have discussed enough for today's class. We should stop here today. If you have any question at this point, you can ask. Please go through the slides and please go through the problems. Okay, otherwise you will not be able to understand. You just hands on the problem. Okay, I will give you some more problems in the next class. Okay, so in the next class we will start with maybe the influence line diagram for truss members, or we will take some more problems of influence line diagram for beams, and then we will move to influence line diagram for trusses. Okay, so do you have any question? If you have any question, please ask. Any question? So should we stop here? Okay. Hello.
Thank you, sir.
Okay. So let us
Okay,
stop
sir.
today. Let us stop today. Okay. So please practice the problems. Okay. I request you always practice the problems. Okay. And whatever problems I am giving in the quiz, through the quiz, you just do it. And if you have doubt, you ask me. Okay. Any doubt, you ask me. Okay. Okay. Thank you. Let us stop today.